Thank you for the kind introduction. Good afternoon, everyone. My name is Hanqing Zhao, and I come from University of Twente, based in Netherlands. And the topic I'm going to present is genome-wide scans for selective sweeps using convolutional neural networks. There are four sections in my presentation. First, I will elaborate our motivation and some basic concepts. Then I will show our framework, the stack. To evaluate stack, we compared it with other current methods in the results section. After that, we will go to the conclusion. In the past few years, the traits of positive selection, the selective sweeps, have already been identified in HIV, and another scientific report reports that the selective sweep identified in influenza A viruses. And very recently, the positive selection also been found in COVID virus. So it is of great significance to detect positive selection because it helps us to understand the forces that drive adaptation. Especially for medicine, it could help us identify the drug-resistant mutations in pathogens and viruses. What's more, it could help to design the more effective drug treatments. So when the positive selection occurred in a population, it will leave its traits, the selective sweeps in this population. The genetic diversity in the neighborhood of the favored allele will be swept away by selection. Here, each row represents a chromosome, while each column represents a SNP. The white circles denote the neutral mutation, while the blacks represent the advantageous mutations. When these advantageous mutations occurs in this population, it will spread very fast and finally dominate this population over generations. And because of the selective sweep, the genetic diversity near the in the neighbor of this favored allele is also decreased. However, the confounding factors such as population bottleneck, migration, and the recombination hotspots will also change the genetic diversity, which generates the patterns similar to a selective sweeps. Thus, these confounding factors might lead to false positive or false negative results in related works. The early approach to address this problem is to utilize the summary statistics. For example, the Taijimus D, Fei and Wu's H, and RAIST. They calculate the summary statistic along the genome, the nucleotide positions, and based on this summary statistics, they find the candidate region. More advanced method like likelihood-based method, like Sweep Finder, Sweep D, and Sweep Finder 2, they calculate certain observation of the summary statistic, and by giving a threshold, they find the selective sweep regions. With the development of machine learning, a software which combined the machine learning method and the summary statistic, it calculates 9 summary statistic and normalizes this in 128 genomic windows. Then, based on a wavelet regression, it obtained the feature of the selective sweep. Another method, DeepLogic, combines the deep learning, the convolutional neural network, and summary statistic. It calculates 12 summary statistic in 11 sub-windows, and then normalize this summary statistic and converted them into colorful images. These colorful images will be the input for the convolutional neural network to do the classification. Although this method have made some achievements, they still have drawbacks. First, the summary statistic-based method, they only detect one of few signals of selective sweeps. And for the likelihood-based method, they ignore the possible correlation of the observations, and some of them require long execution time for the feature calculations. Although SoftWave and DeepLogic, they achieve higher accuracy, they're still sensitive to confounding factors because they are still rely on summary statistics. What's more, they also lack flexibility in scanning the genetic sequences because they utilize the fixed windows. To address the drawback of the current method, we propose a CNN-based framework. We call it's a stack. Here is a framework of our stack for inference, it consists of 3 stages. In the first stages, the raw genetic input data will be represented in binary and then converted into grayscale images. These grayscale images will be the input for the CNN to do the classification. After that, the CNN will output a raw we call profile output, which is a visualization of the probability along the genome. And after that, we utilize post-processing to remove the misclassified results in profile generation stage. Here is an example for the binary representation data. Here, each row contains the genetic information of an individual. And here we convert this data represented in binary based on infinite site model, which means for each allele, it can only undergo one mutations. So here the 0 donates the ancestral state, while the 1 donates the derived state. So this example contains the genetic information of a population with 5 individuals and 10 polymorphic sites. Then, based on a sliding window, we converted the 0 into black and the 1 into gray to generate the grayscale images. The above converted images will be the input for a convolutional neural network of 3 combined layers with 32 filter size and 2 dense layers to do the classification. These 2 figures show the raw output file from the CNNs, and on the left, it's the neutral data set. Here we could observe that some points in the neutral data set was misclassified as a selective sweep. By the way, here the right points represent the probability of neutrality, while the blue represents the probability of selection. For the selection data set on the right, we could observe that the true selective sweep regions is classified correctly. However, there is still some points that is misclassified. To address that, we utilize a post-processing based on moving average to remove this misclassified position. Here is show the neutral data set after post-processed. Here we could observe that the misclassified positions is successfully removed from the neutral data set. And for the selection data set, we also successfully removed the misclassified while the true selective sweep regions remains. The above process is of SDAC for the inference. We also did a custom neutral architecture search to find a convolutional neural network architecture to do the classification. So here it consists of 2 steps. In the first steps, we generate the CNN models of different neural network architectures with SDAC. And then we evaluate these different CNN models based on 3 detection performance metrics, which I will elaborate in the following sections. After that, we find the architectures for classification. So our NAS consists of 6 steps, and in the first 3 steps, we thoroughly explore the combined layers and the filters and the number of the dense layers. From the first 3 steps, we observed 28 models, which is 28 candidates convolutional neural network models. Then in the last 3 steps, we explore the hyperparameters from the training process. We double the size of training sites and the number of epochs. And we also change the number of evolutionary trajectory. Finally, We obtain CNN architectures of 3 combined layers with 32 filter sites and 2 dense layers. So in order to evaluate SDAC, we compared it with other state-of-the-art methods. Our SDAC is built under the framework of with TensorFlows and the Keras, and we utilize a platform of with a 6-core CPU at 2.86 gigahertz with 16 gigabytes of main memories to mirror the performance of each evaluated approach. Here, for the measurement, we only use 1 core to measure the performance. In consideration of the complexity of the real evolutionary trajectory, here we assume the different genetic scenarios. First, we generate 6 different bottlenecks models with varying severity, duration, and beginning time. For migration, we generate 10 migration models with different population join time and a fixed sweep start time. For recombination hotspot event, here we assume 2 different situations. First, the recombination hotspot without sweep, we generate 21 data sites, and another situation is that we generate 10 recombination hotspots with selective sweeps. So finally, in total, we have 101 data sites. For each data site, it has 2,400 simulations for training site and 600 simulations for validation site and 200 simulations for testing site. For the data site of bottlenecks or migrations, we generate the selective sweep at the center of the simulation with selective sweep. And for the recombination hotspot, we generate the recombination regions at the center of the simulations. For the events, for the recombination events that with selective sweep, we also assume 2 different situations. First, the selective sweep within the recombination regions. Here, first we generate the recombination hotspot regions at the center of both neutral data site and selective sweep data site, and then we generate the selective sweep at the center within the recombination hotspot region. And another situation is that we assume that we removed the selective sweep region is still at the center, but we removed the recombination regions of the simulation with selective sweep to the 30 kilobits per position. And we evaluate SDAC based on some evaluation metrics and some reference method. First, we evaluate the SDAC classification abilities against surface wave and dipole shake in terms of F1 score and execution time. And for detection comparison, we compared SDAC against Sweep Finder 2, Sweep D, Omega Plus, and RACE in terms of TPR and 2 other defined metrics, the success rate and accuracy. Here, we define the success rate for evaluation of detection ability. Here, there are 4 simulations, and for each simulation, we generated the true selective sweep position at the center by giving a fixed percentage of the total lines, we got a target regions. If for each simulation, if the position with the highest selective sweep probability is reported by SDAC is within this target region, we say that this simulation is successfully detect the selective sweeps. Otherwise, it is unsuccessful. So for this simple example, the success rate is 3 out of 4. And we also measure the distance of SDAC to the true target. Here we measure the distance between the selective sweep position reported by SDAC and with the true between the true selective sweep position. Here, if the average distance of these four simulations is 10 kilobase pairs, if we assume that the total regions is 100 base pairs, so the distance for this instance is 0.1. And note that for this specific matrix, we expect low values. And here, this is results for classification comparison of SDAC with soft wave and DeepShake. Here is the results compared in the presence of population bottlenecks. Here we observe that these three tools achieve comparable performance for the population bottlenecks. However, the soft wave force was confounded by some specific data sets. For the comparison under migration and the recombination hotspots, they also have similar performance. However, the soft wave was confused by some the old migration data sets, and for DeepShake, it is also severely influenced by the low intensity recombination. Now let's look at the breakdown of the training and the inference times of soft wave DeepShake and SDAC. Here, the DeepShake spends most of its time on summary statistic calculations, and for soft wave, it spends most of its time on training. For the training process, that the SDAC achieve less execution time compared with soft wave and DeepShake. It is like 10 times faster than other tools for training. And for inference, the SDAC still have spend less time on image generation. However, compared with other two methods, SDAC spent more time on CNN inference. The above is shows the performance comparison for classification, and here we evaluate the detection ability of soft SDAC. And this slide shows true positive of the comparison of SDAC with other four detection tools for population bottlenecks. Here we select 10 representative data sites for show the comparison results. And here the y-axis represents the TPR, while the x-axis represents the number of data sites. And here the higher TPR represents the better performance. We could observe that SDAC almost outperformed other tools for all the data sites, especially for some data sets of severe bottlenecks. It have higher performance than others. And for the results of the success rate, here the y-axis represents the success rate, while the x-axis represents the data set. Also, the higher success rate donates the better performance. Although SDAC for some data set, SDAC was slightly lower success rate than Omega Plus and RACE, still for the severe bottleneck data sets, the SDAC still have higher performance than other tools. For the accuracy comparison, here the y-axis represents the distance, and note that for distance, the lower distance represents the better performance. Here we could observe that the SDAC for the severe bottleneck, the SDAC have a much lower distance compared with other tools. And for the simulations with migrations, here we also compare SDAC with other tools in terms of TPR, success rate, and distance. For the simulations with migrations, apparently that SDAC for almost for all the metrics, SDAC have a better performance than other tools. In this slide, we also evaluate whether the recombination hotspot will influence the detection of selective sweeps. So here we measure the effect of recombination hotspots on TPR. Here the expected FPR, the FPR is 5%. We could observe that except the S-stack under the dataset with smaller recombination region size and a higher recombination intensity, that others, all methods were not influenced by the recombination hotspots in detecting of positive selection. And this might, because we use a fixed window size for S-stack, so we have a doubled FPRs than expected. And this is what we are going to do in the next future research. So for the recombination hotspots comparison, also we could observe that the S-stack have a overall better performance than others. However, for success rate, we could see that almost all method was severely affected by the low intensity, by the recombination hotspot, that by the selective sweep that within the recombination regions in terms of success rate. Finally, we utilize our I-stack on Yoruba 1000 genomes, and we identify nine already known candidates genes in human chromosome 1 with top 0.5 TPRs. So in this paper, we proposed a standalone framework I-stack for genome-wide scans for positive selection. We extensively evaluate the we did an extensive evaluation under the various datasets. And I-stack is more robust than other current tools in presence of confounding factors. And for the future work, we will explore more effective image pre-processing to improve the classification accuracy. And for detection, we will also develop more effective post-processing methods. We will also accelerate I-stack inference using hardware accelerators to make it more applicable. And finally, we will integrate I-stack into a standalone sweep detection software. Okay, thank you. That's all my presentations.